Hey everyone, in this lecture I'd like to take a few moments to talk about improper integrals. This is section 7.8 from our textbook. It turns out that there are two different types of improper integrals, so we'll start with what the book calls type 1. And so the idea here is that we have a function, so let's let f of x, or f equals f of x, be a function that is defined on an interval starting at a and then going all the way to positive infinity. So this is like a half infinite or half open infinite interval here, and we want to try to evaluate the integral of this function. Now there's got to be some certain properties about f, but we're going to relate those properties to the actual integral itself. So I'm going to just sketch a possible picture here. So here's our x-axis and our y-axis. Let's say here's our a, that's the left endpoint of the interval, and then the rest of the x-axis here that's showing is the domain of the function. And so maybe the function's even defined over here a little bit, right? And so then the idea is maybe that the function looks something like this. All right, so here's our function y equals f of x. And what we would like to do is compute the area underneath the curve starting here at x equals a, and then continuing all the way out to infinity. So is it possible to compute this area and get a finite number back? Okay, so it turns out that sometimes it is possible, otherwise this question wouldn't even be worth asking, right? But you can also imagine how this would not be possible. So as you're adding more and more x domain here, more and more x values to your domain, you can add so much area, right, that you lose the finiteness of the integral. So how are we going to do it? Well, the basic gist is that we want to make sure that, I'm just going to call this number right here t, so we want to make sure that this number t, for any number t, that this integral that we're used to, this finite integral, exists. All right, so this is going to be our condition on f. We'll say suppose that this integral from a to t of f of x dx exists for all t, let's just say greater than or equal to a, because a, then that gets all of the points in our domain, right? Our domain from a to infinity. Then we can define the integral. So now the idea, you should be able to guess actually what the idea is going to be here. The idea is going to be to take this t, so to take this vertical line here where we said this is our x equals t, and push this t out to infinity. So let t tend to infinity, and then ask ourselves, if we do that, what happens to this integral? It's almost like a partial integral of the integral that we want, right? What we want to know here is the integral from a to infinity of f of x dx, right? That's what we want to know. So how are we going to do it? Like I said, we're going to take a limit, right? We're going to take a limit, all right? So we define, this is called a type 1 improper integral. By the way, the reason this is called improper is because the integral involves an infinity somehow. So type 1 integrals are going to involve the infinity in the limits and the bounds of the integral. So we define this integral from a to infinity of f of x dx to be equal to the limit as t approaches infinity of the integral from a to t f of x dx, right? And then whenever you define something by a limit, you always have to add this caveat and say provided the limit exists, right? Now, if the limit does not exist, so by the way, to even be thinking about this, we've already decided that our partial integrals here all exist, okay? So if the partial integrals exist but the limit does not exist, then we say that this integral diverges, all right? So and if it does exist, then we say it converges. So if this integral from a to infinity f of x dx equals L, so in other words, if the limit exists, then the integral converges, or just converges. Said it kind of weird, but the reason is because if not, so if the limit does not exist, then the limit diverges. The integral diverges. All right, so let's do a couple examples. So again, then we say the integral diverges. All right, I've got a couple examples here just to see how this is going to work, just the functionality of it, and then we can talk about a couple different things that we can do. So let's do examples. First of all, let's look at this integral from 1 to infinity of 1 over x squared dx. What does this graph look like? Well, we're only in the positive x-axis, right? But in general, this graph looks something like, it's got graph over here, right? And then some more graph over here, and it's symmetric over the y-axis. I should be labeling everything here. Symmetric over the y-axis. This is our graph, y equals 1 over x squared. And we want to try to compute, if possible, so we want to know, is it possible to find a finite area from 1 to infinity? So this is the integral that we want to compute, right? And again, the idea here is that we pick some value t, we integrate this up for t, and then take a limit, right? So let's just do it. Once we know the structure of what's happening, the basic philosophical idea of what we're supposed to do, then we just have to do it, right? So this is the picture. Let's see how it works then, right? So we're going to compute integral from 1 to infinity, 1 over x squared dx. By definition, previously, right, that we just wrote down, this should be the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. Now we compute the integral first. We can use fundamental theorem on this because t is not infinity now. T is actually a number. So by the fundamental theorem, this becomes the limit as t approaches infinity of antiderivative of 1 over x squared is minus 1 over x. And then we'll plug in our x equal to 1 as the lower bound and t is the upper bound. All right, and let's see, we still have not done the limit. So this limit is just hanging around until we finish our discussion of the fundamental theorem here. So this becomes negative 1 over t minus a negative, so plus 1. Or this can just, I'm going to rearrange it before I take the limit, but you could just do the limit right now. This becomes 1 minus 1 over t. All right, and at this point, yeah, now you take the limit. So now we're ready to take the limit. All the integral stuff is done, right? And what do we get? We get 1 minus 0. That's equal to 1. 1 is a finite number, so that means that this integral converges, right? And when the integral converges, we will find that, at least in this chapter, we are usually going to be able to, not always. You can't always, depending on how you do it, you can't, sometimes you can say that the integral converges, but you don't know what it converges to. In other words, you don't know what the actual limit equals. But in this case, we know exactly what the limit equals. That's how we got the answer, right? So when you get the answer, 1, you write it down. There will be times, though, when we just want to say converge or diverge. All right, how about another example here? So this next example, I'm going to write slightly differently. So let's do this one from negative infinity to negative 1. 1 over x dx. All right, so this function is a little bit different, and I've also changed the bounds so that now the infinite part of the interval is on the left-hand side, right? It goes to negative infinity. So let's sketch the graph. You don't have to sketch the graphs for these, but it doesn't hurt. So here's our y, here's our x. This function, 1 over x, is very similar to 1 over x squared, except in the left-hand side of the plane, it's in the 4th quadrant instead of the 3rd quadrant. Again, it looks like this. I haven't drawn a scale here, right? So it's not clear how quickly these endpoints are pinching off, right? But what do we want to compute? Well, here is negative 1. That's actually the right-hand bound. And this time, the infinite part is to the left, right? And so this is going to be very similar. This is still type 1. It's very similar to what we did up here. The picture looks the same, except the picture is now down here, right? But geometrically, the idea is going to be the same. What are we going to do? We're going to pick value t right here, right? So now t is between negative infinity and negative 1. And then how are we going to push t out? So we're going to get, partial integral, and then we're going to push t this way, right? Take the limit as t approaches negative infinity in that direction. All right, the other way to do this would be to make a change of variables to get your domain over here. Sometimes that's useful. In this case, I don't think so. I think this is going to be the best way. So let's do it. All right, this becomes what? We have to write down all the steps, right? So first, we rewrite our integral, negative infinity to negative 1, 1 over x dx. By definition, this will now be the limit as t approaches minus infinity. That's what we just drew in this picture, right? We depicted in this picture. The integral is now from t to minus 1, and then the integrand is still 1 over x dx. And now we start, we just look at the integral, right? This is now a finite integral that we're used to. No, I mean, that part's not improper. We're dealing with the improperness of the integral with this limit, right? So nothing weird about that. We know that the antiderivative of 1 over x is natural log of the absolute value of x, and then we're going to plug in our x equal t and our negative 1. All right, and this then, we're still not to the limit yet. We still have to plug in, right? So this then becomes the limit t approaches minus infinity of natural log of absolute value of minus 1 minus the natural log of the absolute value of t. Natural log of 1 is 0, so that term is gone. All right, and so at this point we have limit as t approaches infinity of the natural log of minus t. And remember, the natural log graph looks something like this, right? And even though this looks like it's flattening out here, so this is y equals ln x, even though this looks like it's flattening out, it's not, right? This is slowly growing as x increases. In this case, as t increases, right? And so this is infinite. So that's infinity. All right, by the way, I missed this minus sign. So there's a minus sign here, which means a minus sign here. And just by the picture, it should be minus infinity because it's below the x-axis, right? But the fact that we got a minus infinity here tells us what? That actually, even though this graph looks in some ways very similar to this one, it's pinching down on the x-axis, this one is pinching fast enough that we get a finite integral, right? We get a finite integral, finite area. 1, actually. The area is just 1. This one is pinching so slowly, even though the power is just 1 off, right? This is 1 over x squared. This is 1 over x. And this one's pinching so slowly that actually it doesn't enclose a finite area at all. All right? It goes all the way to minus infinity. And so this one diverges. So that's our conclusion here. Integral from negative infinity to negative 1. 1 over x dx diverges. All right, I have one more example before we get to type 2 integrals, and actually we have something else before type 2 integrals, but this one's going to be the integral from minus infinity to infinity of 1 over 1 plus x squared dx. All right, and so this one I've chosen because, well, I mean, it's probably clear, right, that there's an infinity in both the upper limit and the lower limit of this integral. Now, what we have to do is be extremely, extremely careful with this, okay? So when we draw this picture, so I think we know what this graph looks like. So here's our y, here's our x. This function kind of pinches down. It's very symmetric. It goes through 1, and then it pinches back down. It's supposed to be symmetric, right? And so we want to know, can we compute the entire area underneath this thing? And what we have to do to follow our rule, what we cannot do, let me write this first. Cannot do, and maybe this one is a bad example. I can give us another example in a minute. But what we cannot do is write this as the limit as t approaches infinity of negative t to t. All right, this is a big no-no. Do not do this. And here's the why. So let's just talk about why we can't do this before we even get into this integral. So why? So for that, let's look at another example. And let's say we want to take the integral from negative infinity to infinity of x dx. Well, what's this graph look like, right? This graph is just a straight line. Y equals x is a straight line, slope equal to 1. It does this. All right, and so another question is, what's the area bounded between the x-axis and this curve? So what's that area? Well, if we do this limit like this, right? So if we were to pick a minus t here and the same value of t here, then what's going to happen? By symmetry, this area and this area are going to be the same. Right, so we're going to have that the limit as t approaches infinity of negative t to t x dx. This is just going to equal 0, right? Because by symmetry, this is a positive area. This is the same shape below the x-axis, so that's negative. But that can't be right because look at this. If you take the limit as a, we'll say, approaches infinity from 0 to a of x dx, what happens? Well, if you start at the origin and then you go out a units, right? And then you push this out to infinity, this is going to fill up giant, giant triangle, right? So this one's going to equal infinity and diverge. All right, and so this can't be right. So this is a no. This can't be right. You always have to break up your limits into your infinities into two separate limits if you have two of them. The infinities have to be treated separately. All right, so after that whole spiel, how are we going to treat this, right? So our integral from minus infinity to infinity of 1 over 1 plus x squared dx. First of all, we have to break this integral somewhere. So let's break it at the origin, because in this picture we see we have a lot of symmetry. Well, we're supposed to. My picture's not great, right? But we're supposed to have a lot of symmetry right there. And so let's do it, right? So we write this then as the integral from minus infinity to 0 of 1 over 1 plus x squared dx plus the integral from 0 to infinity. So there's our link, right? And this is a property of integrals. We can do this. And now each one of these is improper type 1. They're slightly different, right? But improper type 1, and we can compute them separately, right? So we can write this one as the limit as t approaches infinity, or minus infinity, integral from t to 0, 1 over 1 plus x squared dx, plus this one can be written as the limit. I'll use capital A again. That's what I used before. A to infinity. 0 to a, 1 over 1 plus x squared dx. And now this is, of course, the antiderivative of arctan. This is the derivative of arctan, right? So the antiderivative of this is arctan. And so here's what we end up with. The limit as t approaches minus infinity of arctan of x from t to 0, right? We still have to plug in. Plus the limit as a approaches infinity, positive infinity this time, of arctan from 0 to a, right? And then we just plug in. So arctan of 0 is 0, but we'll write this out. So this becomes arctan of 0 minus the limit as t approaches minus infinity, arctangent of t, plus the limit as t approaches infinity, of arctangent of a, minus the limit, nope, we don't need the limit there, right? Minus, what? Just arctan of 0. And by the way, even though arctan of 0 is 0, we don't need this, right? Those cancel out. We have plus, we have minus. So we just need to deal with these now. And as t approaches minus infinity, remember arctan's graph looks like this. It's bounded between asymptotes. That's supposed to be, that's a horrible job with the axes. It's supposed to be like that, big point, right? And then that's negative pi over 2 and pi over 2. So this becomes minus pi over 2 plus pi over 2, and that's just pi. All right, and so from this we learn that the integral from minus infinity to infinity, 1 over 1 plus x squared, dx is equal to pi. Obviously convergent then, right? It's obviously convergent. Okay, so next item that we want to talk about, this is something called the p-test. And for this, we're just going to compute, okay? So let's compute the integral from, I'm going to do it as 1, but then we can replace this 1 with anything greater than 0, actually. Let's start with 1, though. 1 to infinity of 1 over x to the power p dx. I want to know for what values of p does this converge. So for what values of p does it converge? And this should remind you of the first two examples that we did, right? We already know. So what do we know? We know that p equals 2 is convergent, but p equals 1 is divergent. So something happens in between there, or maybe 2 is special, maybe 1 is special, right? So that's what we want to find out on this one. So let's just apply the rule, right? So here we go. This has to equal what? The limit as t approaches infinity. Integral from 1 to t of 1 over x to the p dx. And now, so because we already know something about p equals 1, we have to integrate this, right? So because we already know this, let's say when p does not equal 1, then we can apply a power rule here. If p equals 1, we get a natural log, but we already did that, right? We know what happens when p equals 1. So, we don't have to worry about p equals 1. We're going to then integrate this by fundamental theorem, and we get limit t approaches infinity of, this becomes what? This becomes x to the minus p, and then you have to add 1, right? So minus p plus 1 over 1 minus p. Okay, and then we're going to plug in our values. X goes from 1 up to t, and our limit as t approaches infinity. This becomes now x is 1, right? So when x is 1, this is just, sorry, that's the lower bound. So when we plug in t first, right? So t to the 1 minus p over 1 minus p minus, then we plug in 1. So 1 over 1 minus p. All right, as t approaches infinity, this is the only limit that we are worried about, right? So as t gets very large, 1 minus p, if 1 minus p is positive, by the way, 1 minus p can't be 0 because we made this rule, right? If 1 minus p is positive, then this will blow up. So now we have a rule, right? So if 1 minus p is greater than 0, then this limit, so then t to the 1 minus p approaches infinity as t approaches infinity. So that's going to be a divergent, right? So that's divergent. So our integral will diverge if 1 minus p is greater than 0. And then what about the other case, right? So we know that 1 minus p can't equal 0 because that was our conjecture. That was our assumption right here. If 1 minus p is less than 0, though, then this is t to a power smaller than 1. Could be a negative power even, right? And so no, it will be a negative power, right? 1 minus p. If this is t to a negative power, then as t gets very large, this will get very small, right? So then t to the 1 minus p approaches 0 from the right. Well, yeah, maybe not. It doesn't really matter as long as it approaches 0, right? But it approaches 0 as t approaches infinity. And so this one's going to be convergent. And this whole term will become 0. So this will become 0 minus 1 over 1 minus p, which is equal to 1 over p minus 1. Right? And so that's what we get. So here's this is what we call the p-test. We say, suppose p, this one is I put in a box, but this is the one that we want, right? So suppose p is greater than 1, strictly greater than 1. All right, that's the only time it's convergent. It's divergent otherwise, right? Then this integral from a to infinity, 1 over x to the p dx, this is convergent. This is convergent for all a greater than 0. All right, and divergent, so the other side of the p-test is that if p is less than or equal to 1, less than or equal to, right? We got less than from here, we got equal to from here. If it's less than or equal to 1, then this integral a to infinity, 1 over x to the p dx, this is divergent. All right, so we can use that then to just easily help us with some of these problems. So let's go to another one here. We are on to now type 2 integrals. That was number 3. So this is item number 4. So type 2 improper integrals. These ones happen. So type 1 was when the infinity showed up explicitly as an x value. The type 2 are going to happen when the infinity is kind of implicit in the y values. So for example, if your function looks something, maybe it's something like this. Okay, here's our y equals f of x, and the idea here is that it's approaching a vertical asymptote. So in this case, your function approaches infinity in a vertical direction. Okay, so in the y direction, it's approaching infinity. Well, what are we going to do? Let's say we wanted to try to compute the area from 0 to, let's say that this one is at this point where it's undefined. Let's say that this is our a now, right? How are we going to do it? If the function is well behaved up until that point, then what we have to do is, right, take your t, and then what? Push t toward a. But this time t has to approach a from the left because it has to stay within the domain where the function is well behaved. All right, so it's very similar to the other case, except that now you're worried about your infinity happening in the vertical direction. All right, so let's say this. Let's suppose that we have some function y equals f of x has a vertical asymptote, the graph of it, of course, right, at x equals a. All right, and let's also suppose that the integrals, so we have to say this the same way we said the last one, right? So this time it's going to be the integrals from 0 to t f of x dx. These all exist for all t between 0 and a, where a is not included. All right, then we can define the same way. And by the way, you can shift this so that this limit, this lower bound is not 0 anymore, right? But the idea is that these are both finite, right? So then this integral from 0 to a of this function f of x dx is defined to be the limit as t approaches a from the left, from within the domain, of the integral from 0 to t f of x dx. And then what do you have to say? Provided the limit exists, right? Provided this limit exists. If it doesn't exist, we say it diverges. Same way, right? So we can switch this all around. Similarly, what could we do? Well, just by this picture up here, I'm going to go from this direction. What if we have b and we want to try to compute this area right here? Well, now you have to, what? Define your t somewhere here and then push that back, right? Push it back that way. So this time the limit's going to be from the right. So that's the only difference, right? So similarly, I'm just going to write out the formula, but I'll try to do it so that picture's still on the screen. So this integral from a to b f of x dx. The problem here is a, right? The vertical asymptote is the potential problem. So that's the one that we need to use the limit to take care of. So in this time we take the limit as t approaches a from the right. Integral from t to b f of x dx, again, provided the limit exists. All right, so this is the idea with type 2 integrals, and let's do some examples. So we're up to number 5. Examples with type 2. All right, I just got a couple of these. Here's one. This one, integral from 2 to 5, 1 over the square root of x minus 2 dx. All right, so before we do anything else with this, is this one improper at all? So notice with type 2, you cannot see the improperness from the bounds, right? You don't see the infinity in the bounds. So let's see, we're going from 2 to 5, right? So 1 over x minus 2 square root. Well, obviously, as x approaches 2, this is going to become very close to 0. Right? It's approaching from the right, so it's close to 0 on the positive side, and that means that this is going to have a vertical asymptote at x equals 2. So 2 is not in the domain, and then the graph looks something like this. But what we really care about, right, is that from 5 back this way, it's well defined until we get to that asymptote. So there's the picture of what we're going to try to compute here. Again, this is supposed to be the graph of 1 over the square root of x minus 2. All right, let's compute it. So what are we going to do? First of all, let's write down the integral. Let's write down the definition, right? So integral from 2 to 5, 1 over square root x minus 2 dx. Step 1, this has to be swapped out for a limit. This time t has to approach 2 from the right. Must stay within the domain. It has to stay on this side of 2, right? This side. So then this becomes integral from 2 to 5, 1 over square root x minus 2 dx. All right, and so now we have to integrate. This part gets integrated, so we can forget about this for a minute. Well, what's the antiderivative of 1 over square root of something, of u? Well, let's write it this way. Okay, if we put a 2 down below and a 2 upstairs, right, which actually this 2 I'm going to take out and move out here, then this becomes the derivative. So the derivative of a square root is 1 over 2 square roots, right? Derivative of square root u is u prime over 2 square roots of u. So this is just what? This is just 2 times the square root of x minus 2, and then plug in these bounds. Okay, so that should be pretty straightforward. And now, when the upper bound for x is 5, when that goes in, there's no problem, right? So this is just 2 square roots of 3. And then the limit has to stay there for the second bound. So this then becomes the limit as t approaches 2 from the right of 2 times t minus 2. As t approaches 2 from the right, this term becomes very close to 0, right? So this goes to 0. And so this whole limit is 2 root 3, and it worked, right? So we got it. This one converges, in other words. Whenever you get an answer, it means it converges. So that area inside of that little wedge right there, that's a finite area for this example. All right, let's do one more example and talk about something that we need to be very careful about. So in this one, let's say that we have an integral from 0 to 3 dx over 1 minus x. Okay, so when we see this, by the look of it, does not look to be improper, right? Because it doesn't have any infinities in the bounds, but we know that the graph of this, we know what the graph of this looks like, right? So this is another hyperbola, 1 over 1 minus x. Well, what's that look like? It looks just like 1 over x, except it's shifted and it's flipped, right? So this is, so 1 over 1 minus x is equal to negative 1 over x minus 1. So there's a shift to the right, and there's a flip. So we're going to shift this to the right. That'll be 1. And then we're going to flip it over. So the graph looks like this over here and this over here. Okay? So that right there is the graph. Y equals 1 over 1 minus x. What are we asked to find now? We're asked to find the integral from 0 to 3. This is 1, right? So 0 to 1, and then from 1 out to 3. And so notice that now we have actually 2 improper integrals that we have to compute. We have to break this up at x equals 1. All right, so this must be computed as integral from 0 to 1 dx over 1 minus x plus integral from 1 to 3 dx over 1 minus x. Now in our last example where we broke it up, it didn't matter where we broke it. If we scroll back up to that, this 1 over 1 plus x squared, because the graph has no problems, right? We chose to break it here because of symmetry, but then we actually noticed right here that it didn't even matter where we had broken it, because whatever we chose was going to add and then subtract itself back out, right? So up here, it didn't matter where we broke it. Now, for this one, it matters a lot, because look at this asymptote is it's the whole reason that this integral is improper. It's actually the sum of 2 improper integrals, right? So for this integral, the given integral to converge, actually both of these integrals have to converge individually. They have to each individually converge, okay? So let's just do the first one and see what happens. So this integral from 0 to 1 of 1 over 1 minus x dx. This one, the improper part is the 1, right? So this becomes the limit as t approaches 1 from the left. Integral from 0 to t, 1 over 1 minus x dx. And antiderivative here, this is going to be negative log of x minus 1, of 1 minus x, right? So this becomes a limit. T approaches 1 from the left of negative ln of 1 minus x from 0 to t, and then we just plug in. So limit t approaches 1 from the left. When you plug in t, we get negative log of 1 minus t. And then when we plug in 0, you get plus log of 1. Log of 1 is 0 anyway. So this whole integral reduces to the limit as t approaches 1 from the left, negative, right, of the log of 1 minus t. Well, as t approaches 1 from the left, this is the same as the limit as u approaches 0 from the right of log of u, and we know what that equals, right? So that equals minus infinity. This all together, two minuses make a positive. But either way, this thing diverges, right? And you could then argue, well, however it's diverging this way, it's going to equally diverge this way, but that's not good enough, right? That's not going to get you a finite answer. That's not how arithmetic works, right? So the fact that this one portion diverges, the first half of this, right, diverges, tells us that this entire integral is divergent. So that's a divergent integral. All right, one more thing to talk about here, and then this lecture will be over. So this will be number 6. This is called comparison theorem. This is going to be very useful. So this is what I was talking about at the very beginning, or near the beginning, that we will sometimes be able to say something about an integral convergent or not convergent, convergent or divergent, without actually being able to compute the value of the integral. So here's the idea here, and I think this will make sense, but let's suppose that we have two functions. So suppose f and g are integrable functions on some interval, let's say from a to infinity, just for the sake of this argument, all right? And then suppose that that they're both positive. So let's say that 0 is less than or equal to f of x less than or equal to g of x on this interval. So they're not only integrable, but the function g is always bigger than the function f. All right, so let's sketch what these graphs might look like. All right, maybe for example, by the way, I'm going to draw this in a way that we're going to need. So that's going to be the lower one. So let's say this one is our f of x, and then our g of x, let's say, does something like this. I didn't mean to get it so close there. It doesn't really matter. But this is our g of x. So notice that g of x is not always larger than f of x, but it is larger from this point on, right? So there's our a. All right, and so this is the idea now then. So the comparison theorem says that if this is all true, right? So now if we know that the g integral is convergent, so if this integral underneath the blue curve is convergent, if this area is finite, then the area underneath the red one has to be less than that, which means it's also finite, right? So if the integral from a to infinity of g of x dx is less than infinity, so if it's finite, all right, let's just use the words that we just defined, right? So if this is convergent, then the integral of f is also convergent, right? Integral from a to infinity f of x dx is also convergent. All right. The other side of this is, what if the integral underneath the red is divergent, right? What if this one's infinite? Well, the blue one's bigger, right? And so therefore it must also be divergent. So there's the comparison theorem in the other direction. So if the integral from a to infinity of f of x dx is divergent, then the integral from a to infinity of g of x dx is also divergent. Now, what if the integral of f of x is convergent? Can we say anything about the integral of g? And the answer is no, right? So just because this one is finite doesn't mean that the bigger one's also finite. So these are the only two conclusions that we can draw from this. So let's use these to say something about one of our favorite integrals that we, I think, have talked about a little bit. So here's an example. I want to know this integral, 0 to infinity, e to the minus x squared dx. Converge or diverge? So we're going to actually show that it converges. So this is our goal. Show that this one converges. So let's start by sketching the graph over here. This doesn't have to be a good sketch. It can be very rough, right? So here's our y, here's our x. I hope we all know that it's e to the minus x squared. This is the Gaussian bell-shaped curve, right? So this graph looks something like that. So there's our y equals e to the minus x squared. And I want to bound this time by y equals e to the x, because, as we'll see, y equals e to the x is also, when x is 0, it's also 1, right? And when x is, let's do it by e to the minus x, sorry. E to the minus x, because now when x is 1, so there's going to be our a, when x is 1, then these are both going to have the same height, again, e to the minus 1, and otherwise this curve is going to be less than e to the minus x squared there, and then it's going to become bigger out here. All right, and so if we can integrate, if we can show that the integral, so first of all, this integral is finite, right? That's a finite integral. It's not improper. So we can break up our integral of e to the minus x squared to go from 0 to 1. And then from there, what are we going to do? Well, then hopefully we can show that the blue integral converges, because the red integral has to be less than it, right? Just by geometry. So we'll write this then as the integral from 0 to 1, e to the minus x squared dx, plus the integral from 1 to infinity of e to the minus x squared dx. Like we talked about, this one is finite, right? And so this one will use the comparison test. And we'll compare this with e to the minus x. All right, so integral 1 to infinity, e to the minus x squared dx must be less than or equal to, really less than, strictly less than, right? The integral from 1 to infinity of e to the minus x dx. But this is one that we can compute, right? This one we can use our definition, replace the infinity with our limit, right? E to the minus x dx. And then we compute. So what's the antiderivative of e to the minus x? Yeah, it's minus e to the minus x. Plug in our boundaries of 1 and t. And then the limit is going to work on this t, right? So this will become 1. So this becomes the limit as t approaches infinity of 1 minus 1 over e to the t. All right, did a couple things there. Number one, I just switched the order of them, because when you plug in, this first one will be minus, this one will be positive. Then I used the fact that e to the minus t is 1 over e to the t, right? And so what happens? Well, this becomes 1 minus 1 over really big, right? In a limit, well, that's 1 minus 0, so that's 1. All right, so actually this integral, this portion of the integral is less than or equal to 1. Well, guess what? That means it's finite, right? So therefore the integral from 0 to infinity, e to the minus x squared dx, this thing must converge. Converges. And we use the comparison test, right? The integral comparison test for that. Notice, though, that we have no idea. We have no idea what this equals. We just know that it equals a number, right? It converges to a number. All right, I'm going to leave this lecture here. See you guys in the next one.